All right, welcome back. Good to see everyone here this morning. And we're just going to continue with where we were on Monday, talking about multi cycle architecture and then transitioning to how we can take a very similar conceptual breakdown of the design and then increase performance fairly significantly by looking at pipelining as well. Just the administrative note that usually today would be our quiz Wednesday. We're pushing that to this Friday. We're a little behind, and that's okay, but we're just a little bit behind at this point. A week from today is the second exam. The exam is all put together. It's going to feel similar in terms of the way we're taking it as the first exam. I think having put it together, it is an easier exam than the first one. That doesn't mean you don't have to prepare and you don't have to be ready for it. You do have to put some time in to do well on it, but it should be more manageable in terms of time for the second exam. I'm really hoping to see some 100% on that one, and that's perfectly fine with me. That's preferable if we have that on the exam. So we were making a lot of progress looking at both the data path and the control aspects of the multi-cycle processor. And we had a figure along the way that looked something like this, which there's a couple things you want to compare and contrast this with regards to the multi-cycle versus the single cycle data path that you're working on in the lab. First off, there's really only one copy of the major functional elements in this design. So as opposed to having that Harvard architecture of the instruction memory and the data memory, there's just one memory module that we can time multiplex. Same for the ALU as well, right? In your single cycle implementation, you have the primary ALU to do the arithmetic and logical operations that the instructions required, and we have these other little adders kind of scattered throughout to do mostly the branch and jump calculations for those instructions that require the PC updating logic. With our multi-cycle implementation in our data path, because we can have each instruction take multiple cycles, we can now share those resources over time. In order to do so, we need two things. The first is we need these additional state elements in our design here that are allowing us to store the results, the intermediate results of an instruction from one cycle to the next. That's why we have what's referred to here as the instruction register, the memory data register, and register output A and register output B, as well as the ALU output register. So that's an important concept in that we have those registers and they're storing internal processor state. They are there to allow each instruction to take more than one clock cycle. And if you want something to sustain itself over more than one clock cycle, you need to have some sequential storage element. That's what our flip-flops here are for. Our registers are here for that purpose. That's the one major change. Those are different again from our either our program counter or our general purpose registers. Those are our internal state registers. The software wouldn't really have direct access to those. There's probably some ways you could infer the values of those registers using some combination of instructions, but at least directly you don't have access to the values of those registers. As you're designing your processor, you have access in model sim to the values of those registers, but once the chip is designed, that's just internal storage logic to make the processor work. It's not something that's a software accessible register. So that's the one major change. The second major change is that we would have to have additional muxes, or for existing muxes, they would have to become wider for the inputs to those functional elements in our data path. Right? We are now having different ways of having the data flow through this data path, depending not just on the type of instruction, as in our single cycle processor, but depending on what state we are inside a given instruction for our processor. This was just something of a snapshot of executing during the load word or store word instruction, which in some sense doesn't look different than what we have to do for the single cycle equivalent. And remember, the stages of our instruction are still exactly the same. The difference is they're taking multiple cycles now. But this is the stage of execution where we take the register file output, we add it to the sign extended immediate, and then eventually that's going to become the address for memory. So we can see that there's now additional input to the mux that we have here and more potential inputs to this mux down here. The actual operation during this stage is still exactly the same. It's still add base register plus constant offset to calculate our address. It won't be until the next cycle for that load word or store word that will actually be doing the memory operation. That's the fourth stage of that instruction. And so our control then reflects that change as well. For the single cycle processor, I kept saying how your control is a spreadsheet. And that is still definitely the case, right? Given an opcode for an instruction, you can statically determine what all your control signals should be because there's just one set of them and they're fixed. For our multi-cycle implementation, it's going to change on a cycle by cycle basis. Multi-cycle, and this should start to look like a finite state machine, the control changes as it goes from one cycle to the next, from one stage of our instructions execution to the next. So what you ultimately have, and you can think of it this way, as opposed to one global spreadsheet on a per instruction basis, you have a bunch of smaller spreadsheets here that you're selecting between one and the next. So the spreadsheet analogy starts to kind of fall apart here because it is a proper state machine, but that's what's happening in these stages, that you have a very similar set of control signals as in your single cycle implementation. There's just going to be more of them, right? One such example is because this is a single memory module in our design that is at one point acting as an instruction memory and as another point acting as a data memory, and consequently the address input to it will be significantly different depending on if it's an instruction or a data memory. We have a control signal referred to as I or D, instruction or data, that is driving this mux and selecting between, do I take my PC value or do I take the output of the load word, store word, address calculation as my input into my memory for the address port. That's an additional control signal that we didn't need for the single cycle implementation because we had a separate instruction and a separate data memory. And those were effectively, there were some other muxes, but those were effectively hardwired inputs to those address ports. One was an instruction, the other one was an ALU output. And so there's still a similar set of control signals for the multi-cycle implementation. There's just more of them because we now have to kind of multiplex those functional units. We need control signals that change from a cycle to cycle basis to drive those select lines on those muxes. So it is a state machine. Every instruction starts with an instruction fetch. Every instruction starts with a decode. So there's kind of a single edge between state 1 and state 2 here, between fetch and decode. And then at that point, it starts to look a little bit more like your single cycle processor decode path, in which we're going to be doing different things based on what our opcode is now. And that's why we have this kind of branch happening here with multiple edges out of that decode stage. We have the four major classes of instructions. Is it a memory instruction? Is it an R-type instruction? Is it a branch instruction? Or is it a jump instruction? And we want to set our control signals differently depending on which of those instructions it is. And we can actually finish that entire exercise, and this is where we left off on Monday, that there's between 3 and 5 steps for every instruction in our MIPS ISA. And so the number of cycles it's going to take is going to be between 3 and 5 in our multi-cycle processor implementation, with control signals and states in our state machine corresponding to that. And you should just be able to trace your way through it, not worrying, I think, so much about the individual control signals. We're not going to be implementing a multi-cycle processor in the lab, but we start with our signals for the fetch, and then we have our signals for the decode. And then if it was, for instance, to be a load word instruction, we'd be doing our add operation here, just like you are for the single cycle processor. We still have an additional partitioning here because for load word and store word, that third stage is exactly the same. We calculate the address in the same exact way. What we do with that address changes depending on if it's a load word or a store word instruction. If it's a store word instruction, we still need that I or D signal to correspond to data, and we need to write a value into the memory because that's what the instruction does, and then we're done. And then we go back to stage 0 here. If it's a load word, we have a similar signal with regards to reading or accessing the memory as a data memory, but now we're reading from the memory and we're not done. We have that fifth state, that fifth cycle of our load word implementation that is actually going to write the value back into the register file. So in terms of implementing this control, unlike again in the single cycle processor, our data path control signals are not directly determined just based on the opcode. That's what the single cycle allows us to do. But this is very clearly a finite state machine. And we don't spend a lot of time implementing finite state machines in this course. One thing you'll find as an interesting comparison between a course that's doing digital logic design via computer architecture and a course that is doing digital logic design in service of broader embedded systems. Or another way to phrase that in ISU terminology, the difference you'll find between CPRE 381 and CPRE 488 is in this class, we avoid doing any FSM design in VHDL or Verilog. And in 488, that's basically all you're doing in terms of the hardware design that you're doing, because so many interfacing with sensors, actuating with motors, controlling logic in a broader embedded system, it's almost all state machines. And we don't oftentimes need to design our own processor. That's a 381 challenge. We need to work with an existing processor and interface to the other components in our system. That's your 488 challenge. So while we don't do this semester in this class, and you'll have learned a lot of VHDL, you'll still need a little bit more training as you take 48 to learn how do I build a state machine properly using VHDL or Verilog. But that logic diagram on the previous slide is very much a state machine, right? From one state, which would be encoded based on just some storage of a name of a state or some number of bits encoding, plus potentially what our actual opcode is for the instruction. We then determine what potentially our next state is, as well as our output logic, which in this case is our control signals for the multi-cycle data path. We don't know the actual encoding of this. This is something that would then be implementation specific. In VHDL, we don't normally care exactly how that's encoded. We let the synthesis tools take care of that for us, and we just name the states. And that's what a good implementation would generally do. It would have specific names for each of these 10 states in our diagram here, and then that would probably have to have at least 4 bits to encode those 10 different states. But how that would get encoded, what the actual values would be inside this register, is not something we concern ourselves with normally in the design. But this logic is the logic that we would then have to implement, which is given the current state as well as potentially the instructions opcode that we have stored, what should the next state be? What should the output be, which is the control signals for our design? That's a proper Moore machine. So we have our output based on just the current state and can from there drive the rest of the signals in our design. I think when you learn about state machines like in a 281 type course, we think of output as being here's the output to our system, but it's usually not, and the input being here's the input to our system. That's usually not the case, right? Usually the state machine is just some small part of a much larger design that we have, and input and output are just relative to that module itself that you're designing. So this is the output of our state machine. It has nothing to do with the output of our processor, right? The output of our state machine is just these internal control signals. Likewise, the input to our state machine is just these internal control signals through our opcode signals that we have there. But there is a certain uh, uh, design recipe for doing state machines properly in hardware design. And for better or for worse, we don't learn that this semester. You'll have plenty of opportunity if you take follow-on computer engineering courses to learn how to do that properly in VHDL. The challenge, though, and there are multiple challenges with doing a multi-cycle type or style of implementation, is that in reality, we're covering a certain set of instructions, the sort of the textbook set of instructions. We've seen those additional data sheets for all the other type of more complicated instructions that MIPS also would be expected to support. And for any modern microprocessor, the number of cycles an instruction may need to take can vary pretty widely. We still would have our jumps, which could be pretty quick because it's not doing much. It goes from decode to execute and done basically with our jump. But then we have other instructions that can take dozens of cycles depending on what their functionality actually is. This is somewhat related to that RISC versus CISC that used to be a heated architectural debate about how simple you want your instructions to be. Even for processors that have relatively complex instruction sets, they tend to be compiled down at runtime to these micro instructions, to these simpler instructions. The challenge with our FSM-based implementation, our Moore machine from the previous slide, is it works just fine when you have 10 states and between 3 and 5 cycles. Once you get to an implementation that potentially takes 20 plus cycles, the number of states is going to explode in number. And that becomes very unmanageable. It becomes very unmanageable to design and very unmanageable to debug as well. So there's a limit to what you can do with just traditional state machines, not based on the theory of what a state machine is capable of, but just based on what the practice is of how do I implement such a complex state machine and test that it's actually working correctly. That is the limitation. Not anything wrong with the theory, but with the practice of doing implementation and test for it. So, a common design strategy for any kind of decoding of complex instructions into simpler operations is to have this kind of mini instruction or micro instruction or micro op is the other term you will hear used for it, which is doing something very similar. It's defining an additional instruction set, and it's going to be a much simpler one that is defining the individual states of our instructions execution. In this case, it could be still in support of the same exact design, could still be in support of this design, but our control implementation then would not be a finite state machine. Again, it could be, it would work for this five stage implementation, but would itself be a sort of mini processor that has its own internally defined ISA that allows you to take these complex instructions and determine the control signals for that 3 to 20 plus cycle uh, latency associated with that individual instruction. And so instead of a state machine like this, in which you have potentially thousands of states, you would then have a micro program associated with each individual instruction. That would be a micro routine or micro program in which you would define then uh, ways of going from effectively one state to the next inside that instruction's execution. That tends to be not necessarily a public document for modern microprocessors. It's something that is used to implement more complex functionality, but that really goes to some design secrets associated with how those individual instructions can be implemented. But conceptually, we could build such a thing for our, at least for our MIPS processor. For a load word instruction, instead of having a state machine, we could instead have a microprogram. Because all of the steps required to implement, and I'm going to keep jumping back in here, all of the steps required to implement our state machine for the load word could instead be their individual instructions. This would be an instruction that's just setting a bunch of signals. This would be an instruction that sets a bunch of signals and also has a branch. So maybe that's two instructions there. It'd be a branch, right? It'd be a more complex branch or a series of branches because it'd be branching based on what the opcode is doing. And the remainder of these, there'd be an additional branch here, would just be instructions that do those individual operations. Much of which is just setting control signals. Other times we're doing additions and things like that. But that would be an example of what the microprogram equivalent to this would look like. It'd be the same exact functionality. The thought is that it's potentially a more scalable approach. Because while this could potentially grow to thousands of states in our FSM, the microprogram could grow to thousands of instructions, but the total different number of instructions one would have to debug would be significantly fewer. So that is one potential disadvantage of multi-cycle implementation. I think the reason we don't focus as much on multi-cycle versus a pipeline implementation is because it's really just a stepping stone to the pipeline processor, which is taking some of the same design features but improving upon them in many ways here. So in theory, the main advantage of our multi-cycle, as we talked about on Mondays, we were motivating this, is that you're using that clock cycle potentially more efficiently, right? The picture from Monday was we have to set our clock cycle based on our critical path instruction in our single cycle implementation. And instead, now, at least in theory, we could set our critical path based on our longest stage of an instruction. We've split our instructions into 5 stages. Whether that means we have a 5x clock cycle frequency improvement is hard to say, to be honest. But that's the rough attempt of what we're doing. We split it into roughly five roughly equal stages. We've partitioned our critical path roughly into 5. The hope is that our clock frequency would be roughly 5x in a multi-cycle processor versus our single cycle processor. But we know that's rough, right? Because it looks roughly equal in terms of the number of like blocks in our design. Is the actual critical path of those split into 5? That's something we can't even necessarily say until we do some sample synthesis of those designs to know how our clock frequency has changed from a single cycle to a multi-cycle implementation. It does allow a couple things. It does allow us, again, to more efficiently use our clock cycle. It, in theory, would require less overall hardware. We do have to add those additional registers and expand upon our muxes to be able to implement it. But we've saved some other components as well. It would be hard to say for certain the multi-cycle uses less hardware than the single cycle data path, But in that hand wavy kind of way where we look at it and it seems like it does, it probably does. An ALU is much larger than a register in terms of number of transistors required. And if we can truly save on an additional memory, that would be a significant savings. The reality is a lot messier than that, but at least we can look at it and kind of hand wave and say, well, seems like an improvement in hardware resource usage. The downside, though, is that when we actually break down the performance of the single cycle versus the multi cycle processor, it's not all that clear how much performance benefit we're getting from it. The answer is definitely it depends. And I've said that many times, right? The right answer to a performance question is always it depends, but that's not a complete answer. The answer is it depends, and it depends on certain specific things. That's the right answer to that question, almost certainly, right? In this case, as we compare the single cycle implementation's timing for just a pair of instructions versus the multi cycle, we see a bit of a mixed bag here, right? Again, the goal was we take our single long cycle due to the critical path of our load word instruction, and we partition it into multiple cycles relating to the 5 stages of our load word instruction. The argument is being made that we've split it, but we haven't split it exactly right, or maybe those additional state registers make it take slightly longer. That analysis of setup and hold times versus having fewer functional units, we can't necessarily say for certain whether this dashed blue line is actually worse than this first one for the single cycle or not. It seems like our best case, though, is that they're roughly equal. We're still doing the same exact work for the load word instruction. So there's nothing magical about in the multi-cycle implementation it being significantly faster. We have a faster clock rate. And in theory, the savings come in all those other instructions, right? If we compare now the store word, even if the multi-cycle timing is somewhat behind the single cycle after our load word instruction, when we now look at our store word instruction, which is requiring the same exact entire full cycle for the single cycle implementation, for the multi-cycle implementation, it's only taking those 4 cycles now because it only has those 4 stages. We don't need to waste that 5th cycle. So by the time we're on to cycle 10 in the multi-cycle implementation, we're actually on instruction 3. Whereas we're still maybe trying to finish up our second instruction for the single cycle implementation. So the answer is it depends. The more precise answer is it depends on 2 things, right? It depends on what actual clock frequency improvements we were able to obtain. It definitely doesn't seem to be worth it at all if there's no clock frequency improvements. It seems to be worth it if there's a 5x clock frequency improvement, and the reality is going to be somewhere in between. And we'd have to know. We'd have to know that answer to know for certain. The other thing it depends on is then our instruction mix, which was not the case in our single cycle processor, right? Having a CPI of equal to 1 made our life very easy from a performance analysis perspective. Count the number of instructions, that's your performance, or it's some direct ratio of your number of instructions is your performance. Now for the multi-cycle implementation, and as well as when we look at the pipeline implementation, our performance is a factor of our instruction mix. All right, let me rephrase that. Our performance is a consequence of our instruction mix. If every instruction was a load word instruction, our performance would presumably be worse, right? I think we could say that, or it would be no better. And the best case scenario is we're kind of tying our single cycle processor implementation. If every instruction was a jump instruction, which has a CPI equals to 3, we have a much stronger argument to be made that our performance would be better in a multi-cycle implementation because we're taking 3 relatively fast cycles per instruction versus 1 relatively slow cycle per instruction. Again, a clock frequency would still have to be more than 3x better for the multi-cycle to make sense from a performance perspective. In reality, then, whether our performance is better or not depends. Depends on that mix and depends on our actual clock frequency. We did already previous to this a few of those kind of homework questions that talked about that, right? If our CPI is the following, what instruction mix leads to processor A being better than processor B? That's a good type of exam question as well. You don't have to relate it directly back to a multi-cycle data path. I will never ask you to design a processor that has a specific CPI. That's a much more challenging, multi-week step process to do. But given a processor that has a certain instruction mix and a CPI value per instruction type, analyzing the performance of that is something that was from chapter 1 of the book, something that we covered a couple of weeks ago. Very much fair game for a week from today on Wednesday. Questions before we transition to pipelining here? I mean, one takeaway is, well, we did all this work, we built this state machine, and our performance is kind of meh. That's true, and that's maybe the other reason why the book doesn't focus nearly as much on multi-cycle implementation versus what's coming up here now, the pipeline implementation. We're going to borrow some of the best ideas from the multi-cycle and improve upon them to build our pipeline processor. Okay, so part of that motivation is we have those functional units, and generally, we're only using them once per cycle. But if we think about the ALU, for instance, in our multi-cycle implementation, and we go back, and I won't go back to the state machine for it, it's only for certain numbers of those stages in our state machine, or states in our state machine, is the ALU actually doing something meaningful for our design, for the instructions execution. And while there's always data flowing through it, you'll always have signals transitioning in your model sim waveform for it. Only a certain percentage of the time is it actually calculating something that's meaningful to the final result of the instruction. And there's no parallelism there. This is what people were starting to get at on Monday, and there was a couple questions about that on Monday. It is entirely sequential, the multi-cycle implementation. Take between 3 to 5 cycles for the first instruction, and when you're done, now move on to the next instruction. This concept of pipelining really refers to just overlapping of those different instruction stages, with a recognition that they generally, and this is by design, this isn't a coincidence or a happy accident, they are generally independent of each other. And since we have those 5 stages in our MIPS implementation that are roughly independent of each other, at least conceptually, we should be able to overlap different instructions that are at different points of their own execution. Think of it as being multiple state machines that are happening in parallel, but we don't really need to think in terms of state machines to appreciate our pipelined implementation. But that's what it refers to. And we'll go through a fairly tortured analogy in here in just a moment to make sure we appreciate the concept. But at its highest level, conceptually, we're overlapping instructions execution so that we can have multiple instructions using different parts of the data path at a given time. MIPS was designed to, and that was the major design philosophy, to be as clean and as simple of a pipeline as possible. Modern microprocessors, although historically, if you were to actually chart pipeline complexity over time, it's got a very funny inflection point where it was growing, and then we've scaled back actually quite a bit. But modern microprocessors are a mess of deep pipelines for the various instructions they need to support. 5 stages is enough for us to understand the core concepts. When you learn about latest AMD processor that has a 37 stage pipeline, a lot of that is just taking our existing pipeline concepts and splitting them up even more finely. There's a little bit more than that, but conceptually, it's still the same work that has to be done. A load word is a load word under any other name for any other different ISA. The steps of what it has to do is roughly the same across every single ISA for these load store architectures. And so whether it's 5 cycles or whether it's 35 cycles, it's still doing roughly the same work. The difference is how we're partitioning that work to try to improve our clock frequency and to try to get more parallelism out of our design. I can't blame the textbook for this tortured analogy. It is from the textbook, but I chose to continue and use it for class, whereas we could have come up with a better analogy here. So pipelining, you do it all the time. Maybe not today in our current realities, but in theory, in a more regular reality, we would be doing pipelining all the time. So let us assume we have Anne, Brian, Kathy, and Dave, who each have one load of clothes, and they have 4 tasks associated with this. They have to wash the clothes, they have to then dry it, fold it, and then they have to put it away. And there's these different stages associated with it, right? And the equivalent of the functional units associated with each stage. So you have the actual washer, or as they say in parts of Iowa, the actual washer here. that takes 30 minutes to execute. And then you have the actual dryer that then maybe takes also 30 minutes. Then, there's not necessarily a folding machine, although people have tried to build those. There's maybe a folding station and there's just one such table or something that's the folder. Um, and then we have the stasher, I guess, or the actual task of taking the clothes from the folding table and then putting them away in your old school wardrobe that you have there. So I think hopefully you can already start to see where this is going. But this is the somewhat tortured analogy that we will just beat to death today. And then whenever you think of pipelining, you won't think of Ford assembly plants anymore. You'll think of college students doing laundry. If we think of the sequential version of that, um, not necessarily the single cycle version of that, but it doesn't really matter. Either the single cycle or the multi cycle equivalent of this analogy here, the sequential version of that, either way, looks pretty inefficient, right? It's and I already forgot the names. Anne, Brian, Kathy, Dave. Anne starts with her task. She does her entire laundry, and it takes the entirety of the 2 hours because she goes from machine to machine to machine to machine. Maybe she's locked the room, right? No other task is allowed until this load of laundry is completely finished. And then Brian, and then Kathy, and then Dave. That's our sequential or the equivalent analogy to our single cycle or multi-cycle implementation. Whether you think of this as one long 2 hour cycle or four 30-minute cycles is what makes it the single cycle or multi-cycle analogy. But it's the same in terms of the latency associated with it, right? We can kind of see when we're thinking about laundry that that's very inefficient, I guess. And why is it inefficient? Because the stages are roughly independent from each other. As soon as Anne is done with her washing machine, Brian, if his task is ready, if he's available to do so, should be able to get started at that point. And that would be the pipeline version of that. Whereas in the sequential version, if it takes a full 2 hours, if it takes a full 8 hours, for those four loads, each of them taking 2 hours. For the pipeline version, we can see it's taking significantly less, right? 3.5 hours for that same amount of work that's getting done because of that overlapping in time. Because those functional units are independent of each other, we're able to get it done with much less total latency. Something to note, each individual user's latency, or the time it takes for anyone to do their own laundry. Yes, if this was a more realistic example, the second it's done, if Anne isn't there to take her clothes out of the dryer, someone instantly grabs them and throws them on the floor, right? We all know that that's the case. It would have to be in the middle of the night as well. The analogy falls down if you've actually done laundry in a dorm environment. I understand that. But the point I was trying to make here is that the actual individual latency for any of these instructions or for any of the laundry tasks here is exactly the same, right? That hasn't changed. It still takes 2 hours to do laundry. We didn't magically make laundry faster here. We're not magically making our instructions faster on an individual basis when we do our pipelining. Still the same amount of work they have to do. And so it still will take 2 hours or the equivalent number of cycles for our pipelined implementation. But because of that overlap and because of effectively the parallelism that we have there, our speed up is significant. This is showing a speed up of 2.3, which is kind of a funny number. But we could draw this out further, and if we were doing a million loads of laundry, the analysis would be much cleaner. And in the steady state case, you're going to get roughly a nx speed up or an n speed up if you have n parallel components in your design. In this case, 4. We'd have to run this out quite a bit further to see it, but that analysis is an important one to consider. So this is what I just mentioned, right? The pipelining doesn't change the latency of a single instruction or of a single laundry task here, but it does help in our overall throughput or of the latency of the entirety of the task. But throughput in terms of laundry jobs finished per minute is significantly better in the pipeline example than in the sequential example here. And that's our potential speed up, the number of pipeline stages. Where that analysis gets a little bit tricky, and it does get a little bit tricky as we're trying to trace instructions in a MIPS pipeline, is there's that certain latency associated with the time it takes to actually fill that pipeline. It also talks about the time it takes to drain that pipeline as well, but don't double count that. It's one or the other. It's not both, right? the time to take it to fill the pipeline. We see in the steady state here that every half hour we finished a new load of laundry. So our throughput is 2 loads per hour, basically, right? Or 2 tasks per hour we've completed versus a task every 2 hours. So that's our 4x speed up. But in terms of if we were just analyzing 4 here, our speed up is limited by that initial hour and a half that we have to wait to get that first load filled, to fill up that pipeline. Alternately, you can think of it as we have 1 load per cycle starting now, but then there's this additional time it takes to kind of finish up that last person's task or that last instruction that we have. But don't double count it. It's one or the other, right? There's either a latency we consider to fill the pipeline, or once filled, the latency required to drain the pipeline. But it's not both. It's the same amount of time, and it's going to be one or the other here in terms of the overhead associated with pipelining here. Because it takes 4, 5, 6, 7 cycles. That's 4 for the initial pipeline fill plus 1, 2, 3, or alternately, 4 to finish the first cycle plus 1, 2, 3 to drain the last stage. It's two sides of the same coin, but it's not both. It didn't take 10 total cycles here. It just took 7. That does limit the speed up in the very limited, isolated case. And so there's an argument to be made that if we want to be doing laundry as effectively as possible, if we want to have our pipeline as high performing as possible, we want to do everything we can to keep our pipeline full. I agree with that. That's a true statement. Um, but in terms of the analysis of the time it requires to fill or drain the pipeline, that tends to be something that we can amortize out, right? That we can kind of ignore in the steady state. Yes, if you're doing 4 loads of laundry, that is a very meaningful consideration here. And if you're only doing 4 loads of laundry, is this even worth it in the first place to have this nicely synchronized laundry machine happening here? But if you're doing 4 million loads of laundry, then that 3-stage latency to fill the pipeline is roughly irrelevant, right? It's technically there. It's technically part of your performance analysis. It doesn't disappear, but that's why we say we amortize it out, right? When we divide it over such a large denominator, it doesn't really matter. It's a very small percentage overhead associated with the pipeline filling. This is an important concept, though, that we'll keep coming back to it again, and let me connect it directly to instruction execution as well. But suppose we bought a new washer that now takes 20 minutes instead of 30 minutes to do the load. And likewise, I don't know what would make the stasher be faster. New pair of running shoes for the person, putting their laundry away that much faster. That now also takes 20 minutes versus 30 minutes. How does that change the performance of our laundry pipeline? I mean, the answer is here. You don't have to think about it too deeply. The answer is it really doesn't. Right? We're back to kind of that critical path issue, except now it's the critical path of an individual stage versus the critical path of all the stages put together here, right? In fact, this washing machine can take 1 minute, and that maybe helps a little bit with Anne's initial latency for her task. But once we get to Brian, it doesn't really matter. We have to wait for whatever the slowest stage is at that point. He can finish his quickly, but then he still has to wait the full 30 minutes for that dryer either way. You're going to be limited by whatever that slowest stage is. So that goes back to critical path, but it doesn't matter to make one individual stage faster than the rest. In our case, it's a clock frequency argument that the entire design is going to be running at 1 clock frequency. You're not going to have one stage be at 100 megahertz and another stage be at 200 megahertz. There's some allowing for that, but that's more of a semantics argument than a reality of the circuit being designed itself. But in general, it's all running at a single clock frequency here. And consequently, we're really limited by whatever that slowest stage is going to be, both for our instructions as well as for our laundry case here. And for MIPS, we know those 5 stages now. They haven't changed. We'll talk about other laundry approaches as we continue to beat this dead horse of it. I would think if we look at like some of the big concepts of this course, and we've covered I think quite a few. This has been a somewhat deep course at times. This is one of the big takeaways from this course. We've talked about it enough times. Now, as we analyze pipeline processors, it does become fundamental for us to understand it. That there's these 5 stages of execution. They haven't changed. They're the same that you were implementing in Project Part B. How's that going, by the way? I haven't Haven't heard much. I was expecting a lot more activity. Okay, so some thumbs up. Um, this week in lab, everyone should have add instructions working and working within the tool flow. And if you do, you're in good shape. And if you're not, you need to put some more time in. Those 5 stages are still exactly the same, but now that's our 5 laundry stages. These are the 5 cycles we're allowing our pipeline implementation to take. Again, the multi-cycle was doing the same thing, right? With the same exact stages defined in their own way, in the same exact way. The difference now is that was the sequential laundry. This is our pipeline laundry. So we have an instruction fetch stage. So Ann is the first instruction and it's getting fetched. And then the next instruction can be fetching while the first of the previous instruction is now working onto that instruction decode phase. So my point about project part B is this week you should be having single simple instructions working within your processor design because you already had that working previously, right? For lab 4 and project part A, for many of you, you should have it working now within this tool flow. And I was expecting to see a lot more testing framework related questions because there's a little bit of complexity associated with that. That would be a very good milestone to have, for this week, because there's more stuff you have to add. That was my main point. So there's a MIPS test bench we provided. That's I think it's an add I test bench that's just testing different add immediate instructions and add instructions. You should be able to have that working this week. That would be a good goal to have, I would think, and that does require diving into the processor testing framework, and making sure that you get the broad strokes of what needs to happen. The rest is just implementation details. But this concept, this is our big picture concept, one of them for this semester, that almost every processor that one would use would have roughly these 5 stages. That doesn't mean they have 5 cycles in their pipeline or 5 physical pipeline stages. They could have fewer, as we've seen. They can have significantly more, as modern microprocessors tend to do. But if you even look at those modern microprocessors, there'll be some tweaks here and there. There'll be some additional opportunities for parallelism they attempt to take advantage of, but they're still doing those 5 basic things. And as we go back to our timing diagram here, for our MIPS pipeline processor, the idea is, again, connected to that analogy of the laundry, right? The latency of an individual instruction is not actually changing. From the time we fetch a load instruction to the time we are done with that load instruction is still roughly the same as it would be for our multi-cycle implementation, at least. And as we saw, that was still actually pretty close to what our single cycle would be as well. So the latency for an individual instruction doesn't really change. What changes is at least our potential for overall throughput of the processor. How many instructions can we complete in a given chunk of time? Instructions per second should be significantly better here. A couple other things that are different between this and the multi-cycle implementation is just like there was really no performance advantage of, if one user decides that they don't actually want to fold their laundry and they just shove it in a ball in their closet. We've all been there. It doesn't actually improve the throughput of our overall laundry. As long as some people are taking 30 minutes on that table, that's going to limit our overall throughput anyway. So similarly, and in fact, in contrast to what the multi-cycle implementation was able to do, we have these 5 stages defined for our MIPS processor instruction execution. And even instructions that aren't using some of those stages might as well be just idle during those stages. So this is kind of highlighted in blue, at least on the slide that I can see. I don't know how well you can see that. If you open it up locally, you can see the difference in colors here. That's what this is attempting to visualize. It's attempting to visualize both things. First, the overlap of instructions, just like our overlap in laundry. So we will have, as we're debugging our processor, up to 5 instructions that we're actually debugging in parallel. One instruction that will be in fetch, one that will be in decode, one that will be in execute, one that will be memory, and one that will be in write back. And for many of those instructions, since it's only the load word instruction that actually does everything, that needs all 5 of those stages, there will be certain stages that are generating data that's irrelevant for us. For example, the store word instruction doesn't need to do anything in that write back stage. There's no point in ending it early. For the same reason, there's no point in having one person skip their folding stage of their laundry. Likewise, for the R type instructions, it's skipping that memory stage entirely as well. But there's no point in actually, excuse me, it's not doing any work during that memory stage as well. We want to make sure mem read or mem write are set to the right control signals for it, like when your single cycle processor. But there's no point in actually skipping it because we still have to wait for the other instructions that need that stage anyway. So you could think of those as wasted cycles, potentially. It could be thought of as a type of inefficiency, but if our goal of pipelining is to get one cycle, pardon me, one instruction per cycle at a significantly improved clock frequency because we've done that partitioning, then arguably we've got the best of both worlds with regards to our implementation. And let's compare those two things, right? Again, single cycle versus multi-cycle, where we said it was something of an it depends argument, right, with regards to the performance of the two. We saw the advantage of a faster clock frequency, maybe kind of sort of roughly 5x the clock frequency of the single cycle case, but all that latency kind of eating it up anyway. And the overall benefit really being dependent on that clock frequency and also being dependent on the instruction mix as well. The pipeline is an attempt to get the best of both worlds there. The attempt to get a CPI equals to 1, at least in the steady state here, where, yes, there's time to fill our pipeline, so there's that extra plus 4 cycles, at least in the very beginning, or alternately, there's that plus 4 cycles to drain the pipeline at the very end. But in our steady state here, we're getting one instruction done per cycle, getting one laundry load done every half hour here. And so our throughput should be significantly better. This processor is CPI equals 1. This processor, at least ideally, is CPI equal to 1. But it's a CPI equal to 1 at roughly a 5x clock frequency. So while the performance of multi-cycle versus single cycle is a wishy-washy, it depends, for the pipeline processor, it appears to be a win, right? We have finished 3 instructions in the time at which we're still working on the second instruction in our single cycle processor implementation. And just like in the laundry example, where our best case scenario was a 4x speed up over the steady state. If you did 4 million loads of laundry, it would be roughly 4x faster than doing it sequentially. For our 5-staged pipeline processor in the steady state, and assuming we take care of all the nitty gritty implementation details, our performance should be roughly 5x faster than in our single cycle processor implementation. I think a lot of you are already starting to conceptualize what are the headaches going to be involved in both debugging this in lab, that's not going to be trivial, but just in terms of conceptually architecting out the data path for this. But that also leads to a pretty good stopping point for us today. And it's also going to be a bit of a stopping point for us this week. So on Friday, we'll have our quiz. And on Friday, we'll talk a little bit about the data path elements and what they require. And then there's going to be a bit of a gap because we'll do our review next week and then we'll jump back into this topic. And it'll be kind of a seesaw where pipelining sounds great. That's what you'll believe this week. Starting next week, at the end of next week, you realize, oh, pipelining sounds awful. And then by the end, we'll decide that pipelining is actually great again. But it really does depend on how you build in those solutions into your design. Let's leave things here for today. Looking forward to seeing everyone on Friday, certainly for our quiz. And good luck, and do make progress this week on Project Part B. Real legitimate progress in terms of your diagrams, in terms of your spreadsheet implementation. And I look forward to seeing everyone on Friday. Thanks.